Today we are going to formalize notes on the activity that we did yesterday, which incorporates the reading that you had for homework. So we're going to put it all together. I'm going to go through it piece by piece. I need you to write this down so that you have it. This is one of the projectiles that we looked at yesterday. We are now talking about projectiles in 2 dimensions. So the focus of today and the reminder for this entire concept is that perpendicular vectors are independent. Right? Perpendicular vectors are vectors that appear at 90 degrees to one another. The symbol for perpendicular is there in parentheses, which I then utilize through the rest of the discussion. Here we have a ball launched from a cliff. It goes up in the air, comes back down, and lands on the ground well below where it started. As a projectile travels, it experiences 2 perpendicular types of motion. Since they are perpendicular, they can be analyzed separately. And we're going to look at the analysis separately, and then we're going to tie them together. And then later this week, the rest of this week, we're going to do a lab that puts all of this into your hands. So, as a projectile travels, it experiences 2 types of perpendicular motion. Since they are perpendicular, they can be analyzed separately. Those 2 types of motion we talked about at length yesterday, horizontal and vertical. Right? So we're going to take them one at a time. First one is horizontal. Horizontal is the X direction in math class, which is what it is going to be in here from now on. In the horizontal direction, traveling through space, the object experiences no force. As in no push or pull that could affect it in any way, right? This is in the horizontal direction. Therefore, which is the word therefore, but is also the math symbol of 3 dots and a triangle, which I will use later on. The X direction has no acceleration. So to restate, traveling through space, the object experiences no force. This means it does not speed up or slow down in the horizontal direction. Therefore, the X direction has no acceleration. Since the X direction has no acceleration, then we know that the velocity is constant. If the velocity is constant, then V equals d over t describes all horizontal movement. Right? So really, this is your V average formula that we've looked at the beginning of the year, because horizontally, it moves at a constant speed, moves at a constant velocity. So there is no acceleration, so we do not need any of the acceleration equations. This is it. Just like we did yesterday, we can depict the horizontal velocity, using my blue pen here, on the object at all these different locations as moving to the right, the same length, in the same direction, the entire time. This is because the horizontal velocity does not change. Keep in mind, we are dealing with right after we let go of it and right before it hits the ground. We are not talking about interacting with anything else. A projectile is freely moving through the air or through space. So that's the horizontal direction. right? We don't have to go any further because there is no acceleration. We're done, right? The second direction is vertical. Change colors so we can keep things straight. In math class, we learned the vertical direction is y, and we're going to stick to that for now, or forever, right? And in the vertical direction, the object experiences free fall. It's up to you, really. Since it is in free fall vertically, right? Therefore, the vertical acceleration is 9.8 meters per second squared down. Because any object moving through the air only affected by gravity is falling due to gravity. So the acceleration is known. So the calculations are very similar to what we've already talked about. So if we go back to our picture, right, this particular object was launched with some initial velocity. It went up and then came back down. And so we have an initial vertical velocity here that then slows down to 0 at the top, so I don't draw one at the top. Then turns around, comes back down, comes back down, comes back down, comes down a whole lot. It slows down on the way up and speeds up on the way down because the acceleration is always down. But remember, right, free fall with an acceleration of 9.8 meters per second squared, the equations of motion then describe vertical motion. So unlike v equals d over t for the x's, now we're going to be using v equals v naught plus at, d equals v naught t plus 1/2 at squared, and v squared equals v naught squared plus 2ad. Except there's a problem, right? And that problem is fairly organizational, notation-wise. In the horizontal direction, we have movement, we have distance, and we have time. In the vertical direction, we have movement, we have distance, we have time, and acceleration. To tell the difference between v horizontal and v vertical means that we have to introduce something else to tell which v is which, right? And so we're going to do that by changing our notation, right? So in order to separate x's and y's, yep, exactly. The vertical and horizontal movements, etc. We are going to add subscripts to a 2D FOR. And I'll explain what that means. So the frame of reference that we've done so far, right, FOR, has either been up positive or right positive, or other way around, right? Being free to decide on your own. But the problem now is if I say positive 2 meters per second, I don't know if I'm moving to the right or if I'm moving up, because positive 2 could be either of those. So we are going to stick to our math coordinates, and we're going to say up is positive y, and right is positive x, which means that our list of variables is going to be slightly different than it has been. We're going to, in fact, have an x and a y list. So what I mean is that the velocity that moves horizontally is Vx. The velocity that moves vertically is Vy. The displacement that I move horizontally is dx. The displacement that I move vertically is dy, which is often called the height. Could be, but we think of it more as range. How far it will go from the table is its range. Yes. The thing is, right, in this column, in the vertical column, because of the fact that we have acceleration, we have a change in velocity, which means that this final velocity is related to an initial velocity, Vy naught. Initial vertical velocity, Vy naught. Now, second question is, why is there not one for Vx?
Because there's no
because it stays the same the whole time. That's exactly right. Which means that these Vx is really just average V, and there is no Vx and Vx naught, right? There is no initial and final because they'd be the same number, because the same speed horizontally stays the same speed horizontally the whole time. So we've got those, but then in the vertical direction we also have acceleration. So A, in this case, is negative 9.8 because it's known. This is redefined as G, right? For argument's sake, G. G represents gravity, and it is a known acceleration. So a lot of times we will say G as opposed to A to indicate the fact that we're talking about falling. Right. Exactly the point. Okay, so then in both of these lists, what are we missing?
A and V.
Time. There is no acceleration on this side, so the only thing missing is time. Time is independent, but more importantly, the time it takes for this ball to go from here across to here is the time it takes for this ball to go up and come back down vertically, because it's all one ball. The time it takes to go from here to there is the time it takes to go across and is the time it takes to go up and come back down. Time is not a vector. It does not contain direction. Time is common to both directions.
I have a question.
Common. Time is common to both, because the time it takes the ball to go up and come back down is the time it takes to go across, because it does all of that all at the same time.
Is that the last one?
So, if I take this list of variables and I apply it in this sense to the equations that we've got, right? I can regenerate my equations list in x and y terms. Right? So in the x direction, we only have v equals d over t. And so now to rewrite it, it's vx equals dx over t, where this is the average velocity, and most importantly, is the only equation because it moves at a constant velocity horizontally. In the vertical direction, rewriting these v equations, vy equals vy naught plus g times t. dy, or the height, equals vy naught t plus 1/2 gt squared. And vy squared equals vy naught squared plus 2 times g times dy. They are the same equations, listed with slightly different notation in order to keep separate x's and y's.
You don't have to memorize these, right?
Never.
Wait, is that a
Sydney.
V? Is that a Vy squared?
Yes. Go back and look at this. all I did is add y's to the underneath and change a to g. Right? I changed nothing. I just rewrote it so that we're talking about vertical only. In your homework, get out your homework. You have your homework number 1. Number 1 had a rock thrown horizontally at 5 meters per second off a cliff that was 78.4 meters high. There were 3 questions. I'd like to go through 2 of them with you today. So first, this is the picture, right? And after our discussion yesterday, you should note that this goes like this in an arc and hits the ground. We are talking about the moment right after it was launched and right before it hits the ground while it's in the air, right? So far, all I have are these 2 variables and not a lot of information. So it seems barren, but it's not if you take your time and think about a couple of major details, right? First of all, I think X was horizontal. This was thrown horizontally, which means that this is Vx. This is vertical, right? The rock is going to go down, drawing an arrow that goes in that direction, 78.4, which makes this dy. I also know that A is AY, which I'm now calling G, because the only acceleration experienced by a projectile is gravity while it's in the air, is 9.8 meters per second squared. Down. So, if it's negative, then we need to start and say up is positive y, and to the right is positive x, which makes this positive 5, this negative 78, and this negative 9.8. The rock falls down, gravity is down. Furthermore, and probably most important that you overlooked, if I have thrown it horizontally, I did not move it vertically. So what is the initial vertical velocity? 0. Vy naught is 0 as a consequence of being thrown horizontally. That is a context clue that will not be obvious. If I throw something horizontal, I didn't throw it vertical. If I throw something vertical, it doesn't move horizontally.
So why do we need to know that Vy naught is 0?
All right, so go to our list. List of variables. Vx is 5. Dx is unknown. T is unknown. It should be obvious that I can't do much with the horizontal because I have 2 unknowns and only 1 variable. That doesn't help me much of anything. But that is the extent of the variables in the x direction. Those are it. In the y direction, Vy naught is 0. Vy is unknown. Before it hits the ground now, Vy is unknown. Dy is negative 78.4. A is negative 9.8, or G is what I started to write, which is why that got messed up. And T is what I'm probably going to have to look for. The first question on the homework said, if you throw a stone horizontally at a speed of 5 meters per second from the top of the cliff, how long does it take the stone to reach the bottom of the cliff? We're looking for the time. We cannot find the time here because we don't have enough variables. So we can use the y to find the time. So if we say dy equals Vy naught t plus 1/2 gt squared, right? We have all of those variables, and we don't have Vy. This does not have Vy in it.
Oh, I thought we were trying to find...
That's the third question.
Okay.
One at a time. It is most useful to find the time first because time is common to both sides. So dy we just assigned is 78.4 negative. Vy naught is 0 times t is still 0, plus 1/2 times negative 9.8 times t squared. This is negative 78.4 equals negative 4.9 t squared. Half of 9.8. 0 times t is 0. I then divide by negative 4.9. The book has chosen this number beautifully because this comes out to be exactly 16. Many of you made the mistake on the quiz. T squared equals 16. You do not divide by 2. You take the square root, and 4 is t. The time it takes is 4 seconds. All right, but look, since this is now 4, this goes here and here, right? So the second question is, how far from the base of the cliff does it hit the ground? Here's the base of the cliff. How far is dx? So dx is in the vertical or the horizontal equations, and there's only one equation. Vx equals dx over t. V is 5, dx, t is 4, dx equals 20 meters. So the idea is, right, I can find the time it takes to hit the ground because the vertical is the reason why it hits the ground.
Yeah.
The horizontal is not, because if there was no gravity, it would never hit the ground.
Go like that.
Once I know how long it takes to hit the ground, I can then share that information with the horizontal, because the time it takes to go across is the time it takes to go down, because it goes across and goes down at the same time. Once I have that, I can plug it into the horizontal equation and solve for dx. Oops. The third question says, what are the horizontal and vertical components of the stone's velocity just before it hits the ground? Now here's the thing. What is the horizontal velocity just before it hits the ground?
5.
5. Because it's 5 the whole time.
Because the velocity would stay the same.
Horizontally.
Horizontally, yeah. Okay.
Exactly the point. So that means that you already know Vx equals 5. That was the answer to that part, horizontally. So then the question is, what is the vertical velocity just before it hits the ground? Well, I would assume that since you now know time and you know every other variable, all you have to do is solve for that, and that's the answer. So for homework, see if you can find Vy, and then retry number 2 for homework, and we'll talk about it briefly tomorrow, and then the rest of the week we're going to put all this together in a lab where you actually tell me where this mark is.